Welcome back, everybody. Let's continue to talk about measures of variability. In the last video, we talked about how to compute the standard deviation for data from an entire population. We learned how to compute sum of squares both using the definitional formula and the computational formula. And at step 2, we computed population variance, symbolized with a sigma squared, and population standard deviation, symbolized with a sigma. In this video, we're going to learn how to compute standard deviation based on sample data. And it's really almost exactly the same. One thing that's going to differ that I mentioned in the last video is simply the symbols. So instead of seeing a mu, a population mean, if we're dealing with sample data, we're going to see an X bar in the formulas. That's a sample mean. And then at step 2, we won't be computing population variance, we'll be computing sample variance. Instead of computing sigma squared for population variance, we'll be computing S squared for sample variance. And then, of course, instead of computing a population standard deviation, we'll be computing a sample standard deviation. Instead of computing sigma, we'll be computing S. So just some symbols are changing. That's no big deal. There is, however, one formula that changes just a little bit. You might have noticed this already. At step 2, when we compute sample variance, instead of computing a basic average of the squared deviation scores, we compute a modified average of the squared deviation scores. Instead of dividing by n, we will divide by n minus 1. So it's not a very big change. It's really no big deal. But I want to make sure you understand why we're going to make that change. Take a look over here for a second. Imagine that this distribution, which is perfectly normally distributed, represents IQ scores. So right around the middle is an average score of 100. Here are people who are really smart, who have IQs like over, 130. And on the left side, here are some people who struggle a little bit intellectually. They have IQs less than 70. Think about this entire number line. There's a lot of variability in the entire population. And of course, a measurement of variability, like the standard deviation, should be able to capture all of that variability that exists in the population. But because there are so few people out here on the high end and so few people out here on the low end, depending on our sample size, particularly if it's not a very large sample size, they might not get to be selected for our sample. So one thing that we know is that even when we randomly pick people to be in our sample, the variability that we see in a sample tends to be less than the variability that exists in the population. That's a problem because unless we have some type of correction, the sample standard deviation would be a biased estimate of variability in the population. The sample standard deviation, if we had no correction, would underestimate the variability in the population. So we need to do something to correct for that bias. And there's actually a very simple correction that over the long run leads the sample standard deviation that we compute to be an unbiased estimator of population variability. In other words, this very simple correction that we're going to use in the long run, it works. And that correction comes at step 2 when we're computing sample variance, S squared. Instead of simply taking an average of the squared deviation scores, in other words, instead of taking sum of squares and dividing by n, we're going to take sum of squares and divide by n minus 1. Think about this for a minute. I just told you that sample variance tends to underestimate population variance without a correction. The correction that I just explained to you divides the sum of squares by a smaller number, n minus 1. If I divide sum of squares by a smaller number, the sample variance that we compute will be larger. That's the basic point that you need to understand. When I divide something, like the sum of squares, by a smaller number, the answer that I'm going to get for sample variance will be larger. That n minus 1 correction that we see right there is actually pretty common in many of the formulas that we will see throughout the semester. And in fact, it has its own name. We call it degrees of freedom. So sometimes the formula for sample variance is written sum of squares divided by degrees of freedom. Let's go ahead and replicate this example right here. We'll work on it together. In this example, we're going to assume that we have sample data, and we've also been asked to compute sum of squares using the definitional formula. So that's what we'll do. Just by looking at the formula, I can already put together a plan for what I'm going to need to do. I'm going to need to compute these deviation scores, so I might as well have a column for deviation scores, x minus x bar. That's how much every single score differs from the sample mean. And then before I sum anything up, I need to take those deviation scores and square them. So let's have another column, x minus x bar, those are the deviation scores, squared. Looks like the first thing we're going to need to do is compute the sample mean. Let's go ahead and do that. X bar equals the sum of x divided by n, our sample size. And you can see our sample size equals 1, 2, 3, 4. Let's go ahead and compute the sum of x. 6 and 3 is 9, plus 9 is 18, plus 6 is 24. So we have 24 divided by 4, which equals a mean of 6. Let's go ahead and subtract 6 from every single value. 6 minus 6 equals 0. 3 minus 6 equals negative 3. 9 minus 6 equals 3. 6 minus 6 equals 0. Remember, if we've done this right, these deviation scores should always add up to 0. When dealing with these nice round numbers, I like to just take the positive numbers and compare them with the negative numbers. If I add up all the positive numbers, I get 0 plus 3 plus 0, which equals 3. Add up all the negative numbers, I get negative 3. So they cancel out, they clearly sum to 0. We must be on the right track. So those are all the deviation scores. I need to find squared deviation scores. So let's go ahead and square each value. 0 squared is 0, then we have 9, 9, and 0. Now we ask ourselves, do we have a column labeled with what we've been asked to sum up? And we do. So let's go ahead and sum it up. In this case, we'd find that sum of squares equals 9 plus 9, which is 18. It's that easy, my friends. Sum of squares for sample data and population data is exactly the same. All that we changed was the notation that we were using. Instead of having a mu in our formula, which is the population mean, we have an x bar, which represents the sample mean. Now that we know that sum of squares equals 18, we can go to step 2 and compute sample variance. We're going to take sum of squares, which is 18, and now divide by n minus 1. We saw that n was equal to 4. 4 minus 1 is 3. 18 divided by 3 equals 6. So sample variance, s squared, equals 6. Let's take a minute to remind ourselves that at step 2, when we're dealing with variance, whether it's sample variance or population variance, we're still dealing here with squared deviation scores. We want to know, on average, how much the scores differ from the mean. We don't want that measurement to be based on squared deviation scores. So that brings us to step 3, when we compute the standard deviation. All that we're going to do at step 3, regardless of if we're dealing with population data or sample data, is simply take the square root of what we did in step 2. In this case, we're going to take the square root of the sample variance. The square root of 6 is 2.45. That, my friends, is our sample standard deviation. That is S, the sample standard deviation. How do we interpret that? On average, these scores right here differ from the sample mean by about 2.45 points. Let's go through one more example with sample data. But in that example, instead of using the definitional formula for computing sum of squares, we'll use the computational formula for computing sum of squares. We'll replicate this example right here. Let's change views and we'll do it together. One nice thing about using the computational formula for sum of squares is that I never need to compute the mean. I only need to find the sum of x squared, and I need to find the sum of x from my data. Once I have those values, I can plug them into that formula and compute sum of squares. So I'm going to need to know the sum of x squared. Let's go ahead and create a column for the squared x values. And let's go ahead and square every value. 6 squared is 36, 8 squared is 64, then we have 0 and 36. Let's find the sums of each of those columns. The sum of x equals 14 and 6 is 20. And then the sum of x squared equals, I'll use my hand calculator to help, 36 plus 64 plus 36 equals 136. At this point, all we need to do is plug those values in. So sum of squares equals the sum of x squared, that was 136, minus this fraction that we see right here. In the numerator of that fraction, we need the sum of x, that quantity squared. The sum of x, that quantity squared, would equal 20 squared. And 20 squared equals 400. So in the numerator, we have 400, and we need to divide that by n. Keep in mind that we have 1, 2, 3, 4 different data points. So our n equals 4. All we need to do now is simplify and solve that. We're left with 136 minus 100, which equals 36. So the sum of the squared deviation scores in this example equals 36. Once we know the value of sum of squares, everything else is really very easy. Let's move to step 2 and compute sample variance. When we compute sample variance, we're computing a modified average of those squared deviation scores. So instead of dividing by 4, which is what n equals, we will divide by n minus 1. In other words, we will divide by 3. 36 divided by 3 equals 12, so variance equals 12. Because variance is telling us the average squared deviation score, it's not telling us exactly what we want to know. We want to bring that measurement back down into standard units, and that's what the standard deviation is all about. So all that we need to do to compute the sample standard deviation is take the square root of the sample variance. And in this case, the square root of 12 equals 3.46. So we've learned that the standard deviation of this data right here is 3.46. On average, these scores right here differ from the mean by 3.46. As that value is larger, we have more variability in our data. As that value is smaller, we have less variability in our data. We've gone through 4 examples already, and I'm sure you see they're all pretty much the same. You need to get to the point where you can master one example. If you can master that one example, then you can compute standard deviation in any situation because every example is essentially the same. The only thing that differs is the data that you start with. Well, I think that's enough for right now. In the next video, we'll talk a little bit more about the characteristics of the standard deviation and how we plan to use the standard deviation in the future. So I'll see you in the next video. Until then, be safe.